Okay, so in this section, I just want to show you how to do a couple different calculations for your homework. The first one is going to be binding energy per nucleon, and I'm just going to go through the steps that it takes to solve this kind of calculation. So notice that we have binding energy per nucleon, and it's mass defect times the speed of light squared over the number of nucleons. So this first example problem here, to help you with solving your problems with your homework, they want you to find the defect and binding energy per nucleon of a helium atom. So how do you do that? Well, first you need the mass of protons, neutrons, and electrons, and you want to multiply each by the number of particles for that isotope. So we have 2 protons for helium, we have 2 neutrons for helium, and then we have 2 electrons. So I'm going to essentially double each number, and when I double each number I get 2.01455,294, and that's AMU. And then when I double the neutrons, I get 2.0173284. I'm sorry, 2984. And that's AMU. And then 2 electrons, remember they're the smallest, so it's 1, 2, 3, 4 zeros, and then 5, 4, let me just double check this. I'm sorry, I have 3 zeros, not 4. Okay, so 5, 8, 4. I'm sorry, 5, 4, 8. I can't. 4, 8, 5, 8. And that's AMU. Okay, and then when you add up all 3, you get 4.0324, 3136. So this is the theoretical mass, but what actually happens is this is what we call mass defect. So we find that there's a missing energy. So you want to take the mass that you just calculated, so 4.0324, 3136 AMU minus, they say that the mass that you actually have is 4.00260,325. And when you subtract the two of them, you get 0.02982811 AMU. Now we want to convert it from AMU to kilograms, so we're going to use this relationship. So 0.02982811 times 1.66054 times 10 to the negative 27 kilograms, and that's per AMU. So when we do that, we get 4.95308 times 10 to the negative 29th, and that's in kilograms. Now we want to find the binding energy per nucleon. So we're going to go back to this over here. So we're going to take the kilograms that we got, so 4.95308 times 10 to the negative 29th, and that's in kilograms. We're going to multiply it by the speed of light. So 299792458, and that's meters per second. And make sure that's squared. And we're going to add up the 2 protons plus 2 neutrons because we want nucleons. So when you do that, you essentially get 1.11290 times 10 to the negative 12. And because that's energy, we're going to call it joules per nucleon. Okay, so that is how you do the binding energy and the mass defect. So the second one was binding energy, just to let you know. Okay, so I'm going to skip the section we talked about particles and rays, and I'm going to go into actual processes so that when you do the problems on the homework, you know how to solve for it. Okay, so here is alpha decay, and they typically will give you the isotope, but they don't give you all the other information. So you have to look up on the periodic table what is the atomic number for uranium. And after this section, you're probably going to know it by the top of your head just because you'll do it all the time. So we have 4,2 helium, which is our alpha particle. Now please remember that you want to subtract 4 from 238 because you want to make sure that you're conserving mass. And then because you have 92, you're going to subtract 2 from that, and that gives you 90. Now the thing you want to do is you actually want to go to the periodic table and see what is the symbol of the new nuclei from beta decay. And when you look at it, it's thorium. Okay, so here is beta decay, and we're starting with iodine. So it has it has a mass number of 131. You have to look up the atomic number for that on the periodic table, and it is 53. And because it is losing a beta particle, it's going to have a -1 charge. And please remember, there's no mass change, so we keep 131 as our mass number. But our atomic number goes up, so we actually gain a proton, and as a result of it we have atomic number 54, and you want to look that one up, and on the periodic table that is xenon. Now here the next one is a positron emission. So notice we're starting with not carbon 12 but actually carbon 11, and when you look for its atomic number, notice that it's 6. Now a positron, the difference is the mass number of a positron, because it's the size of an electron, is 0. And it's actually a positively charged electron. So there's no mass change. It stays at it stays at mass number 11. But because of conservation of mass, its atomic number has to go down. So it loses a proton, and as a result of it, it becomes boron. Okay, and then the last one here is electron capture. So we want to look up rubidium's atomic number. When we look up rubidium, it's 37. Now we have to add the electron to the reactant side because it's capturing that electron. And then to predict the fixing my symbol here. To predict the product, all you have to do is add up those two numbers. And remember, there's no mass change here, so it stays at 81. And because you're adding a negative number, the atomic number goes down. And as a result of it, you get 36. So you have to go to the periodic table and find which element has atomic number 36, and that is krypton. Okay.